So our next talk is by Alex. He's gonna talk about SPTO in open quantum systems. Please go ahead.
Okay. Well, first of all, I'd like to thank the organizers for giving me a chance to share this with you today. What I'll talk about is some work in collaboration with Caroline de Groot and Norbert Schuh. It's an idea that Trong referred to in his last talk and is closely related to it. But as he explained, it's a slightly different physical context, and hopefully I'll provide a new angle on these ideas. The questions I want to be asking are, what are the topological phases of open systems or of mixed states? I'll focus on a subset of that, which is first to consider the topological phases of closed systems or pure states, and then see what happens to them when they're subjected to a coupling to an environment. Which of those phases are robust against the coupling or survive. And in particular, I'll focus on the simplest of topological phases, which are SPT phases. Before getting to any sort of classification or study of robustness of phases in open systems, it's important to have a working definition of what a phase is. So in closed systems, there are several perspectives on this. One can speak of paths in the space of gapped Hamiltonians. Another perspective, which has been shown to be equivalent, is to think of fast local evolutions between states. So thinking less of the Hamiltonians and more in terms of their ground states. And in the quantum information community, typically one replaces this fast local Hamiltonian evolution with an approximation by some low depth circuit made of local gates. For open systems, some progress was made in this paper by Coser and Perez Garcia in generalizing the second of these two notions of phases. As far as I know, the paths in the space of gapped Hamiltonians isn't something that's been generalized to open systems. But for the second notion, the idea is to consider fast local Lindbladian evolutions between mixed states. And a new fact about Lindbladians as opposed to Hamiltonians is that they're not necessarily reversible. So there, the equivalence relation is that you can go from one state to the other by some Lindbladian evolution. There's also a Lindbladian evolution taking you in the other direction. These are not necessarily inverse of each other.
As an outsider to open systems, what is a Lindbladian?
It's a generator of an evolution satisfying some conditions. So it's like weakly coupled to the environment and satisfies a Markovian assumption. Yeah.
As another outsider, is it okay for me to think about this like in the context of finite temperature systems where rho would be like e to the beta h? Is that the case of this? Or
I think these results won't quite apply to finite temperature systems. Yeah.
Is there a simple reason why that's a bad choice with rho? Or?
Let's see. I'm not sure if the assumptions involved in the Lindbladian formalism are always satisfied. Yeah.
Yeah. So correct me if I'm wrong. So actually, I consider the system and the environment together.
Yeah.
Entire Hamiltonian should be unitary.
Yes.
Now suppose that just because it's the northern environment, then like effectively get some evolution which is described by this Lindbladian.
Exactly. Mm-hmm. And of course, these are just definitions, but what they show in this paper is that this is a good definition to try to build a classification from, because it has some nice properties like local observables are analytic within phases. That's at least the basic thing that you would want for your equivalence relation. Okay, so I want to enrich this notion of phases with symmetries. So how it works in closed systems is that we consider paths in the space of symmetric gapped Hamiltonians. Or in the second perspective, we consider fast local symmetric Hamiltonian evolution. In terms of gates, this means that the low depth circuits are built out of symmetric gates. But if we try to generalize this to open systems, it's not obvious what symmetry conditions should be imposed on the Lindbladian evolutions. So there are kind of two natural guesses. One, which is called weak symmetry, is just that this operator script UG, which conjugates the density matrix by the symmetry, just commutes with the Lindbladian, the generator of the evolution. Another, which we call strong symmetry, says that the adjoint of the Lindbladian annihilates the symmetry generator. This one's a little bit less intuitive, but it ends up being somewhat more correct. And these two notions of symmetry are closely related to the average and exact symmetries defined in Chung's paper. Though again, the physical context is a little different. So in thinking about which of these is the more appropriate notion of symmetry, I want to think about dynamical versus static notions of phases. So a dynamical definition of a phase asks which states can be evolved into which states according to an allowed evolution. So we say two states are in the same phase if there's an allowed evolution going between them. The static notion says that two states are in the same phase if they have the same values of order parameters. So for SPT phases in one dimension, we have nice order parameters. We have string operators that work for pure states, and we can take them as a way of defining phases for mixed states as well. Then the question becomes, which symmetry condition on Lindbladians is such that evolutions satisfying the symmetry condition have string order constant along the evolutions. That is, the static notion of the phase equals the dynamical notion of the phase. So with that behind us, I can get to the main claim that I want to make, which is that SPT order, if we define it according to string order parameters, is preserved by these evolutions precisely when the evolution satisfies a strong symmetry condition. And it's worth noting that this, at least superficially, seems in contradiction to some claims that have been made about average SPT order. But as I'll talk about in a later slide, this is because we're using a slightly different notion of what it means for a phase to be preserved.
Actually, a very quick comment. Actually, so there's a generalization. The string order parameter, we can define a average SPT, which will be more consistent with what Chung was defining.
Is there?
Yeah, right. You might talk tomorrow. So.
Oh, okay. Okay, that's very curious.
So, but I fully agree with you. If we use the old definition of string operator, then this SPT will vanish once you make the symmetry weak.
Yes.
Yeah.
So I think there are two ways to read this result. The conservative one is that it's just a rule for determining how string order behaves under evolution. So maybe you don't want to evolve the state and recompute the string order on it. You just can instead look at whether the evolution satisfies the symmetry condition. If it does, you're guaranteed that your string order is the same as it was initially. But secondly, one could take it as a good definition of SPT phase equivalence. So we can talk about two states being in the same phase if they're related by one of these strongly symmetric evolutions. So let me say a little bit more about these two symmetry conditions and give several perspectives on them. So first, I want to talk about how weak symmetry is not strong enough. So in this paper I mentioned by Coser and Perez Garcia, they construct a fast local Lindbladian evolution that takes any 1D state and maps it to a product state. So clearly this is destroying SPT order. So it looks like there are no SPT phases in one dimension until we realize, well, there should be some symmetry condition imposed on these evolutions. It turns out, however, that this Lindbladian that they define actually does have weak symmetry. So our only hope is that there's maybe some stronger symmetry condition on L that could protect SPT order in open systems. So what I want to work with are not Lindbladians, but channels. I'll always have in mind channels that are generated by Lindbladians, but everything I say is just true for general channels. So a channel is a completely positive trace preserving map. Every channel has a representation in terms of Krauss operators, K. And an example of a channel is just a reversible channel. So that's one where I have a single unitary Krauss operator. And the Krauss representation of a channel is not unique, but it's unique up to some unitary operation, just changing the basis of the Krauss operators. So let's write out the weak symmetry condition in this language. So first of all, I originally wrote the weak symmetry condition in terms of the Lindbladian. In terms of the channels that it generates, the weak symmetry condition looks like this. Written out in terms of Krauss operators, we get this first line in the bottom box. What this means is we have two Krauss representations of a channel. So that means they must be unitarily related. We can choose a basis of the Krauss operators where that unitary is diagonalized, and we get a bunch of phases, e to the I, theta I. So one thing to notice here is that each of the trajectories, so each of the Krauss operators, could in general be getting a different phase. So that's something a little bit weird, that we get this interference in phases between the trajectories. So a natural guess of what to do to preserve the SPT order is just to set these phases to be the same. And when we do that, the condition ends up becoming basis independent. And in fact, one can argue that for nice channels, so ones that are generated by Lindbladian evolutions, the phases actually vanish. And we get the condition that each Krauss operator individually commutes with the symmetry generator, as opposed to just the channel as a whole. So that's what I'll be calling the strong symmetry condition. Comes from getting rid of this interference between the trajectories. So one small comment, these two notions of symmetry only ever had to come into play because we're dealing with mixed states and open systems. If we considered only unitary evolutions, then these two conditions agree, because there's only one Krauss operator. So commuting with the Krauss operator is the same as commuting with the channel as a whole.
Alex, quick question. Does a reversible channel necessarily means a single unitary?
No, wait, that's okay. Reversible is the wrong word here.
Oh.
Yeah. So jumping back to Lindbladians, just as channels can be expressed in terms of Krauss operators, Lindbladian can be expressed in terms of these L sub i's, which are called jump operators. The Lindbladian is then just this usual Hamiltonian evolution plus these corrections, which represent its coupling to the environment. So using the connection between the Krauss operators of the channel and the jump operators of the Lindbladian, we can rewrite the strong symmetry condition in terms of the jump operators. So it essentially reads that the Hamiltonian is symmetric and each of the jump operators individually are symmetric. So this is just much stronger than the Lindbladian as a whole being symmetric. And it's worth noting that this condition has appeared previously in these other papers, though not in the context of SPT phases.
I think you might have just said it, I didn't get it. What are you assuming about the jump operators? What kind of operators are they? Conditions and what they are?
No.
Random operators.
They're
not Hermitian, they're not anything.
It can be Hermitian.
Huh?
It can be Hermitian.
Well, I mean, but you don't have to assume that they are.
I don't think you do.
No, for example, it can be, it cannot context.
But you want them to be local, presumably, for your definition of phase equivalence, right?
Right. So far, everything is just in the abstract with no notion of locality. But eventually I'll be interested in Lindbladians that are sums of local terms. And then the jump operators of those local terms will of course be local. Yeah. So the jump operators are not unique for a Lindbladian. It's just that every Lindbladian has this description. And for any description, we can characterize the symmetry condition in terms of jump operators. So just to build more intuition for how the two symmetry conditions differ, here's another perspective. So since we're interested in order parameters and their expectation values, it's nice to work in the Heisenberg picture, where instead of evolving some arbitrary state, we can just evolve a fixed order parameter, in this case, the string order parameter, by the adjoint channel. So in this language, what the strong symmetry condition means is just that the symmetry generator is fixed by the adjoint channel. So physically, this is the statement that charge is conserved in the system alone, as opposed to the total of the system and the environment. In terms of the Lindbladian, we get the condition that I wrote on one of the earlier slides, which is that dual Lindbladian annihilates the symmetry generated. Now, one other perspective on the two symmetry conditions, which gets close to the definition that you'll find in Chong's paper on average SPT phases, is in terms of purifications. So for every channel, there is some purification that one builds by enlarging the system by appending some ancillas and representing the channel as a unitary evolution on this larger system, followed by tracing out the ancillary degrees of freedom. So in terms of the purification, what weak symmetry means is that the purification is symmetric under some symmetry action on the system and some other symmetry action on the ancillas. Strong symmetry is that, but we require that the symmetry action on the ancillas is trivial. And one can give a more physical interpretation of the statement. If we think of the evolution as, if we think of the purification as some Hamiltonian evolution, so W written as the exponential of a Hamiltonian on the system and the back, and that Hamiltonian is written as a sum of these tensor product terms between the system and the environment. What strong symmetry means is that each of these terms individually means with the symmetry. So that's what the two symmetry conditions are. Now, before building to the result, I want to say a few words about string order parameters. I think a lot of this will be review for almost all of you, so I'll just go through it quickly, but I'll be putting it.
Don't assume.
Okay. I'll go through it at medium speed. Okay, so SPT phases in one dimension are completely characterized by patterns of symmetry fractionalization on the edge. So when you act on just a region of the system with the symmetries, does nothing in the bulk of the region, but you get these operators acting on the edge of the region. And in total, these two operators need to form a linear representation of the symmetry. But if one just looks at the left side or the right side individually, the action of the symmetry can be projective. So this projective action VG has an extra phase omega GH that can appear in it. And it turns out that this is a group cohomology class. So these classes characterize the symmetry fractionalization patterns of 1D SPT phases. Now, this is kind of an abstract argument. The point of string operators is to basically measure what the symmetry fractionalization pattern is in terms of expectation values of some operator that you can just apply to the wave function. It's useful to think about all of this in terms of tensor networks. So in one dimension, since we're dealing with gap ground states, we can efficiently approximate them with matrix product states. So a symmetric state is one where you act on it with the symmetry and you get the same state back. Let's represent each side of that equation with a matrix product state. One has tensor UGA and one has tensor, the original MPS tensor A. There's a nice result about matrix product states, which says that if we have two tensors representing the same state, they're related by a gauge transformation. And this tells us that this symmetry U fractionalizes on this bond dimension, bond space of the tensor, and that's where these projective representations appear. So where string operators come in is extracting the class of those projective representations. Going forward, I'll just assume G is a finite abelian group. As we saw in previous talks, the string operator is just acting on some bulk of the string with the symmetry and acting on the ends with some charged operators. It turns out that the expectation values of these things obey a selection rule, also called a pattern of zeros. So usually the expectation value vanishes unless a certain constraint that relates the charge of the end operators, the cohomology class of the state, and the symmetry acting on the bulk is satisfied. When that selection rule is satisfied, it's some non-zero value. How this works for matrix product states is that we sandwich string in between the MPS, bra, and ket, apply some manipulations to these diagrams, and the result of that is that the string operator evaluates to just this trace of this thing ng written here and the end operator of the string. This thing generically is non-zero as long as ng has the same symmetry charge as the end operator. So the end operator we assumed has some charge, which we called alpha. This operator ng, its charge is essentially the charge of this virtual symmetry Vg, which happens to be omega over omega. So that's where we get the selection rule that alpha equals omega over omega.
What is space NGX on?
Space. Oh, what the space? So this tensor network has two legs coming out. So it's the space of density matrices.
So O can be any arbitrary operator as long as it transforms, as long as it is some charge.
Yes, as long as it has charge alpha. And there's like a measure zero set of end operators with charge alpha that are non-generic in that they interact with the MPS tensor in precisely the wrong way, where you get some accidental zeros in the pattern. So when I talk about the pattern of zeros, I mean the selection rule you get when you choose a good generic end operator.
And sorry, I actually forgot, what was alpha again?
So alpha is just some representation of G. So it's the charge of the end operator.
Alpha is the representation.
Yeah.
And when you write alpha equals omega or omega, that means what you wrote above, h comma g divided by g comma h.
Yes. 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 So that's what I had.
So there's a ruler over there that used to point. And also a laser pointer.
Okay.
If you want.
Okay. I think I'm
Easier
free
to
to
get
parse
easier to
whatever
see
you need that,
the
but-
mouse pointer.
Yeah. Okay. So, okay, this is essentially just explaining why we get a selection rule in the expectation values of string operators.
Wait, sorry, just
Mhm.
so ng again is something that is just determined. You literally do this calculation and you find what ng is. Is that
Yes. Yeah. Mhm. Yeah. So it's a function of A, the tensor representing the state, and well, it's actually just a function of that because this Vg is also coming from the tensor.
Oh yeah, there's a figure, yeah.
Yeah. So we have a bunch of these string operators parametrized by symmetries in the bulk and charges at the ends of the string. And if we measure all of them and record the results, we can write down an array. So for every G label in the bulk of the string, there's a unique charge that we put at the end such that the expectation value does not vanish. So let's mark that point in the array with a star. Everything else in the column will vanish. And now when we look at these arrays as a whole, we can tell what phase the state is in. So for example, when the symmetry is Z2 cross Z2, there are two phases, the trivial phase and the Haldane phase. So for the trivial phase, you get a pattern that looks like the one on the left. For the Haldane phase, you get a pattern that looks like the one on the right. In general, when your symmetry group is bigger, these are, of course, harder to write out. But all you need to know is that the knowledge of all of these values determines the ratios omega over omega. And moreover, in the finite abelian case, if you know all of these ratios omega over omega, it uniquely determines the cohomology class. So you can determine which phase you're in just by looking at this array. So one comment I'll make is that if you're interested in non-abelian symmetries, then you need more order parameters rather than just strings. But these have been constructed.
So.
Yeah.
Just to be clear, so in these matrices,
Mhm.
let's say for the holiday case, the rows are representations of, so like of SU2, right? Is that what it is?
Z2 cross Z2. Yeah.
Okay. And the columns are just like to 4 elements of Z2 cross.
Right. Mhm. Yeah, so there's some pairing between group elements and charges. That is a function of the co-cycle defining a fractionalization pattern. Okay. So now we're ready to talk about how strong the symmetry condition on channels interacts with string order. And there's a general story one can tell about a large class of channels. So these are causal channels. In particular, this includes channels that can be written as finite depth circuits of local channels. But for the purposes of this talk, I just want to focus on a very special class of channels. And then the argument only takes 3 slides. So the special class of channels are what I'll call uncorrelated noise. So you just have a channel acting site by site. So what strong symmetry means on these channels is, of course, that each of the on-site pieces is strongly symmetric. Now, if one looks at how this acts on string operators, one sees that, well, on the bulk, the string operator is just the symmetry UG. The strong symmetry condition says that's unaffected by the action of the channel. At the ends of the string, there is a transformation that happens, but you'll always get some new end operator that has the same label alpha. So the channel doesn't affect the labels of the string operators. Conversely, if the labels of the string operators are unaffected, the channel must have been strongly symmetric. So that's what happens on the level of the operators. Now we look at their expectation values and states, and we get the result that for any string order pattern of zeros, Lindbladian preserves that pattern precisely if it's strongly symmetric. So one direction is to ask, is the pattern preserved if we have a strongly symmetric channel? The answer is yes. We just showed that the labels of the string operators are preserved. And now if we're restricting to generic end operators, that means that the patterns of zero is also preserved. This happens unless we choose particularly bad end operators that are annihilated by the channel. It's also worth commenting that this result works at finite times. Weird things can happen at infinite time evolution where some of the end operators get annihilated.
What do the zeros represent?
I'm sorry?
What do the zeros represent? Any string order pattern of zeros? What's the pattern? What there are zeros and non-zeros. What are non-zeros? What do they mean?
So the zeros are values of G and alpha such that the string order parameter vanishes. The star are values where it doesn't vanish. And the particular non-vanishing value it takes doesn't matter. That's if you pick different end operators, you'll get a value there. But the important thing is the selection rule, whether that value is 0 or non-zero. So it's kind of a weird way of encoding the cohomology class of a state. But it's a nice way of encoding in that you can read it off simply by looking at expectation values of operators.
Are there as many? Is every different single order pattern of zeros? Is it different? Or I guess I'm just asking, is the classification literally how many ways of that can't be right? Is that true?
So some of them are not allowed.
Oh, okay.
So for pure states, like one constraint is that every column has to have exactly one star. I'll talk about in a later slide that weird things can happen for mixed states. So like average SPT phases will violate this rule. But I think that's an interesting question to ask, what are all the possible patterns of zeros? And can you think of that as some classification of mixed state phases or So just. Right. Then the last thing that needs to be shown is that suppose the string order is preserved. Did we need to have strong symmetry in order to do that? And the answer turns out to be yes. If we think about the string order parameter as this sandwiching of the string operator in between the MPS and its dual, that is evaluated in terms of this transfer matrix, which is this E dagger UG sandwiched in between the MPS tensor and its dual. And in order for this thing to be non-vanishing in the limit of long strings, this transfer matrix has to have a maximum eigenvalue 1. And it turns out this only happens when the thing that's sandwiched in between is a symmetry. So what that tells you is that the channel acting on the symmetry generator is at least some other symmetry generator of the MPS. The final piece of the argument is to realize that we're interested in Lindbladian evolutions. So there's this continuous path from the trivial channel where clearly E dagger maps the symmetry generator to itself. And this channel at finite time, this implies that this sigma, which permutes the symmetries, has to be 1. So we get that the E dagger on the symmetry generator is just E dagger. We get that we must have had strong symmetry if all of the string order parameters were preserved. So finally, I'll just talk about some recent related results and draw some connections between them. So in Chong's paper, they talk about average SPT orders. They have a section that is more relevant for what I've been talking about than what we heard in the last talk. So these are systems that evolved where a subgroup of exact symmetry, which is essentially strong symmetry, but also with an average symmetry. So the evolution is only weakly symmetric with respect to this second piece. Nevertheless, they find that some SPT order is preserved. And these follow-up papers use string correlators to argue that this SPT order that's preserved really is real SPT order, and that you can detect it with these other order parameters. So it's natural at this point to ask, how can these evolutions, if they're not strongly symmetric, but they only have strong symmetry with respect to part of the symmetry and weak symmetry with respect to the rest, how can they preserve SPTO? And I think the answer is that these channels wash out some of the strings, but they nevertheless preserve SPTO in some other sense. So if you take, for example, symmetry as Z2 cross Z2 and make the first factor be an exact symmetry and the second factor be an average symmetry, the strings that have average symmetries in the bulk just get washed out. So like the two phases that I mentioned before, which are shown on the left, top and bottom, these are the patterns of zeros of the pure states corresponding to some state in the trivial phase and state in the Haldane phase. But they get evolved under channels satisfying this half exact, half average symmetry condition into the patterns on the right. And these patterns never arise for pure states. They're special patterns of zeros that only these mixed state average SPTs can satisfy. And in some sense, we can talk about the original SPTO being preserved because it can just be reconstructed. It's clear just by looking at the pattern you get on the right after the evolution, what you must have started with. But in more complicated situations, that's a full reconstruction is not possible. Okay, so I'll just close by talking about some future directions. So one thing I'd be interested in is thinking about what the symmetry conditions mean in realistic open quantum systems. So maybe in some context, the strong symmetry condition is like unphysically strong or not something we can expect. Maybe in other contexts, it's reasonable, in which case there is order that's preserved under those couplings to the environment. Another direction is kind of along the lines of this question that was asked: what's the classification of mixed state SPT phases, including these average SPT phases? Is it correct to think about them as corresponding with just patterns of zeros? these that satisfy some weaker constraint than the pattern of zeros for mixed states. One has like not just the patterns of these average SPT states, but also things like a mixture of two SPT pure states with different SPT invariants. This also gives you an exotic pattern of zeros. But I wonder whether there are any phases of mixed states that go beyond even those two possibilities. Another direction is what happens in higher dimensions. So at least if you want to take the approach that I took in this talk, where you're looking at order parameters and using them as sort of a definition of what a phase is, you need some analog of a string operator in higher dimensions. And as far as I know, that hasn't been constructed, at least kind of the natural guess of taking a membrane where you act with the symmetry on the bulk and put something on the edge. At least I haven't got it to quite work out. I think this should detect like the slant product of the 3 cocycle and then a lot of these arguments would go through. But if anyone has any thoughts on how maybe to make that work, I'd be interested in chatting about that. Yeah, and then finally, I think there's a question of what are these SPT mixed states physically? Like, can we think of them as what we get by just evolving with certain Lindbladian and obtaining a steady state? Yeah, so I'll wrap up here.
So do we know an example of SPT, any of this that's like you can realize that it's a steady state of Lindbladian?
I don't know. Yeah.
So, and a related question, if the steady state is the identity of an enlargement, is it all trivial?
It's also like the maximum mixed state. Yes. It has, yeah, I guess so. The pattern of zeros of that is just a single star in a corner. So it's trivial in some sense, but it has a different pattern than a product pure state. It's trivial in a different sense. Yeah.
Those of course are different phases under.
If by phases you mean string order pattern of zeros you get, then yes, they're different phases. Because for a pure product state, no matter what symmetry you have in the bulk of the string, you can find some end operators where you get a non-vanishing string. But for the maximally mixed state, just the mixture washes out the bulk of the string. So it's going to vanish no matter what you put on the ends.
Is there anything you can say about the boundaries or edges of these states?
I'm not sure. Yeah. Yeah, it's hard to talk about the degeneracy if you don't have a Hamiltonian. So yeah, I'm not sure.
Well, you can still talk about like correlation functions, evaluate the boundary, like still a well-defined thing for the matrix.
Okay. Yeah.
I guess I was wondering, maybe it's related, and this is a bit open. Have you thought of any connection to quantum error correction for these things? That seems a bit relevant, maybe in that case. You're thinking of, some time evolutions which are, so I can think of like these as noise that's entering the system, but if it's symmetric in a certain way, you're still in the same phase. These are just words, but I don't know if that's the connection that you thought of.
Yeah, I guess these aren't topologically ordered, but like maybe if you're doing measurement-based quantum computation on SPT phases, then you care whether the SPT order, which is crucial for that procedure working, to be preserved under whatever noise you have.
Right.